Cool, thank you. I'm Diogo. As a bit of background, I have a very math and computery background, which is very good for deep learning. List of achievements on why you should listen to me is that I currently work at a super cool company that uses deep learning to make faster and more accurate medical diagnoses. And in the past lives, I've won a whole lot of international math competitions and some programming competitions as well. And today I'm going to chat about what deep learning is and what it can do for you. Feel free to ask questions at any time. If I can ask that, right? They can ask that, right, Simon? Yes. Cool. So yeah, feel free to ask questions at any time. Just yell them out, especially if you think I'm lying to you. So what is deep learning? Going to start with a disclaimer. Deep learning is actually pretty complicated. It's hard to be very general about everything and be correct. So when in doubt, I'm going to favor generality. So if you're familiar with deep learning already, it's going to sound like I'm lying a lot. But in reality, this is just to kind of give the really high level of it. And also, whenever possible, I'm going to favor some of the shortcuts that might not be 100% correct, but should give the correct mental model of how these things work. But if you have any questions, feel free to ask. So from a super high level, there's a lot of different levels of hierarchy here in the ecosystem. There's artificial intelligence, which is a superset of everything. An example would be IBM Watson, where it's lots of hand-coded rules and uses extremely large amounts of expert manpower built to do a specific task. There's machine learning, which is a subset of that. An example of this would be Google ad-click prediction. And how you do this is rather than using tons and tons of hard-coded rules, you start using more examples to figure out how to combine some hand-coded statistics to predict the probability of, for example, an ad click. At a slightly deeper level, you have representation learning, which is sometimes seen as one-layer deep learning. So sometimes referred, these levels are called shallow learning if you're trying to start a fight. And an example of this would be Netflix movie recommendation, where the statistics of what you even know about each movie is learned from data, but you're still learning a simple combination of how these features go together. And after a few levels, you get into deep learning. So this would be an example of figuring out diseases from images, where instead of having a layer of manual statistics that are learned and then combining it together, you might learn all of these statistics at the same time in tens, hundreds, or even thousands of steps, which is what some people use nowadays. This is probably not a common view of what deep learning is, but I think the easiest view of how to see it is deep learning is just an interface. And this interface has roughly two methods. As the first method, you have a forward pass. And this is definitely the easy part. Given arbitrary input, make arbitrary output. Anyone can do this part. This is really easy. The trick that makes it work is the backwards pass. So given a desired change in the output, you want to be able to transform this into a desired change in the input. And once you have these, you can make arbitrarily complex things by chaining them up into a directed acyclic graph. This sounds too good to be true, especially with how we designed the forward pass, because if you just say arbitrary input and arbitrary output, of course you can do anything you want. But the hard part is how you define that backwards pass, because as you make your forward pass more and more complicated, like if you have some really crazy function, it becomes hard to define how to map the inputs back into outputs. So by keeping these things simple and combining them together, it gives us this almost composable language of modules that allow us to do the things we want to do. So once you have this interface, you just can build up from this. Once you have that, you code up a bunch of these modules that satisfy this interface. As a side note, a bunch of these modules will be parametric, which means that they have parameters, which roughly means that they're stateful. And they're stateful means that once you have the state changes, and it's this change in state that allows you to change this function from something that you just cobbled together to something that gets closer and closer to what you want to do. And once you have a framework, a language of what you want to do, now you can start doing the tasks that you care about. In deep learning, you always define a loss or a cost, depending on how you want to define this, and this is something you want to minimize. For reasons that I'd happily explain, this has to always be a scalar. So it can't be several costs at the same time. You have to squash it down into a single thing that you care about. And once you squish this number, like everything you care about in the world, into a single number, now you can start using deep learning to optimize this. You create an architecture, which is the function that you want to do, and this would be how you compose together these modules that I talked about. So the way you connect them together changes the function that you have and the kind of representation power it has. And that becomes the hard part. After that, you initialize the parameters, and you train this architecture by repeatedly updating the parameters to minimize the cost. So you go forward through the network to get the things you care about, and you go backwards through the network to change the parameters to be slightly better for your cost. And you repeat this many times until you get a function that you're really, really happy with and solves whatever problem you want. And at the end, you just use that function, just the forward pass. How to implement the backwards pass is, in general, we almost always use the chain rule. This is really nice because it makes implementing the backwards pass easy. How this works is if you have your output as some function of some x, and you have the partial derivative of your output, dldf, you can get dldx by simply multiplying the partial derivative of df/dx. And the nice part about this is that dldf is gotten from the rest of your network, and df/dx is gotten just from your module. So this allows you to chain these things together in a way that only requires local information in order to get this backwards pass. It's very nice. There's theoretical reasons of why this is a good way to do this. And perhaps the best part about this is some frameworks make this completely automatic. By defining a forward pass using automatic differentiation, you can figure out how to make a backwards pass automatically. So it becomes basically as easy as defining arbitrary functions. So you actually do get this benefit of just define arbitrary things, return arbitrary things. As long as all the operations you do are differentiable, you can just make it work like magic and optimize it. And this is literally how people do this in practice. Updating the parameters, these are just minor details to get an understanding of how this works, is that once you have your existing parameters, you get your gradient, and you take a step in the opposite direction of the gradient. And the partial derivative tells us how to change the parameters to increase or decrease the cost that we care about. An important word to know, though, is that people always use, that I think kind of makes it more complicated because it's a big word, is backpropagation, or backprop for short. This has a longer name called reverse mode automatic differentiation, which sounds pretty complicated, but this is just the chain rule plus dynamic programming. I assume that, I just talked about chain rule, I assume people are familiar with dynamic programming, but this is just caching. And the idea would be, when you have a computation graph, this is a very simple computation graph, E equals C times D, C equals A plus B, D equals B plus 1. The idea would be, you traverse the graph from the top to the bottom, and by doing it from the top to the bottom instead of the bottom to the top, you can cache the intermediates that are used many times in the graph. And by caching these intermediates, you get something that's much more efficient than if you were going to do a naive solution. And this allows you to get gradients that are computable in linear time in the size of your graph. So you basically evaluate each node once, and this is a really nice property. This makes it all really efficient, and that's basically it for the basics. From a high level, deep learning is just composing optimizable subcomponents. Optimizable almost always means differentiable. Differentiable means that you can do backprop. Backprop is just the chain rule in dynamic programming. Once you get into practical deep learning, normally you have to combine this with gradient descent software and a data set that you care about. And the space of software is, there's a very rich space of software that I'll talk a little bit about in the future. But these things are solved for you. So you can do deep learning without even knowing how to calculate a gradient yourself. So while we can do arbitrarily complicated things, there are a few standard modules that are the main workhorse of deep learning today. And the goal of this section is going to be to get a high-level understanding of each, since all of them can be very incredibly nuanced. But these standard modules will cover almost all of what's happening in papers. The simplest of them is, perhaps the simplest, is just matrix multiplication. It has many names: the fully connected layer, sometimes shortened to FC, sometimes called dense because you have lots of connections, linear layer because it's a linear transformation, or affine because sometimes there's a bias. And The matrix multiplication is basically every time you have a neural network diagram, all of these arrows correspond to the matrix multiplication. So when you have a diagram that looks complicated, that's from this kind of thing. And you can interpret this as a weight from every input to every output. So if you have m inputs and you have n outputs, you have m by n weights that transform your inputs to your outputs. And its implementation is literally a matrix multiplication. And W, in this case, is generally a parameter, which means you learn the connections from inputs to outputs. This on its own is not powerful enough, so you need at least one more thing, which is nonlinearity. The original nonlinearity is called a sigmoid. It's just this function. It has the nice property that it maps reals into the space 0, 1, and it can be interpreted as a probability, but that's not as important as just being nonlinear. And the reason the nonlinearity is important is if you have this kind of neural network, when you stack up the layers back to back, if you had no nonlinearity in the middle, this would just be 2 matrix multiplies back to back, and what would happen is you could just combine this into a single matrix multiply. So if you had a 100-layer, purely linear network of just matrix multiplications, while this thing is pretty complicated and you do all the work of a real neural network, you could actually flatten it into a single weight matrix because of the composition of linearity. So this was the original one. People like it because it's very similar to what people used before they really got how machine learning worked, which was just binary thresholding. It was very brain-inspired back in the day. And the cool part is, with just those 2 units, you know how to make a neural network. You can just simply you get your input, you apply the matrix multiply, you apply a sigmoid, you apply another matrix multiply, and you have one. And these are called multi-layer perceptrons when you only have matrix multiplies and nonlinearities. And the cool part is that there's a theorem on this, that this simple architecture, like literally 3 functions, can approximate arbitrary functions, which means it can solve any problem that you care about. There's a cool theorem on this. The idea is that if you make the middle big enough, you can calculate basically any function. The downside is that just because it can, it doesn't mean it will. And a single-layer, multi-layer perceptron often causes more problem than it solves. So this is why there was an AI winter in the 90s, just because these things are kind of terrible. But people have gotten a lot better at it, so now neural networks are cool. And as a disclaimer, these are neural networks. When you have, so this would be a multi-layer perceptron. These are neural networks. Everything I'm talking about today is still a neural network, but these are specifically, when you talk about the multi-layer perceptron, that is what this is. So since then, people have made better nonlinearities. This is probably majority of the improvement between 1990 and 2012, unfortunately. Which is, you have like a kind of a smarter nonlinearity. So instead of taking this weird squiggly function, you just do a threshold. So anything that's negative, you just turn it into 0. This is actually the most popular nonlinearity nowadays. It does incredibly well. It has some really nice optimization properties. In particular, when you have 0, this nonlinearity is very linear, so it works very well with a chain rule. And this thing is used almost everywhere nowadays, especially in the middle of a neural network. There is a softmax, which you can think of as converting a bunch of numbers into a discrete probability distribution. So the math of it is p equals, you exponentiate your input, and then you divide it by the sum of the inputs. You can think of the explanation as turning all of the numbers into positive, and the dividing by the sum is a normalization term. There's some very nice properties about this, and it's used as the final layer for classification problems, and it's used in almost every neural network. Cool, that was the easy part. This gets complicated. Feel free to ask questions during this. I normally explain this with a whiteboard, and it normally is complicated even with a whiteboard. But I'll try to go through this. So a convolution is the main workhorse for deep learning on images, and deep learning on images is it's kind of where this revolution started. So it's very, very important. It's probably the place where deep learning is the most advanced. So it's a very important primitive, and I think it's a very cool primitive to understand. Because you really realize how beautiful the framework is when you see wow, this thing sounds pretty complicated, but it you can just plug it in, and you don't even need to know how it works when someone has coded it up for you, which is what I do. So this is a linear operation for 2D images. So once you have a multi-layer perceptron, you have a mapping from every input to every output. But in the case of images, your inputs are structured. So you have like this spatial relationship between your inputs. And if you have a mapping from every input to every output, you kind of throw away this spatial relationship. So the idea would be, what if, rather than having a connection from every input to every output, what if every output, the output looked like an image as well, and every output was only locally connected to the things it corresponds to? So that is insight number one, so local connections. And insight number two is, every output is a local function of its input. What if, instead of having every output be its own function, which would be the general case, what if every output was the same function of its input? So what this then becomes is equivalent to like a well-known function in computer vision, which is a convolution, which is you have a kernel, which is, you can think of it like a local weight matrix. So it's represented, let me see, oh cool, my mouse is here. So it's often represented as this square in an image-like thing, which means that they're capturing that local input. You just do a matrix multiply between all of the weights of the kernel, which would be something like this. You do that multiply for everything in the local region. You sum up the result, so this is just a dot product. And then you do that at every single location at the input. So it's kind of like tiling your input with the same function, or it can be interpreted as extracting the same features at every location, which is the more common way to interpret it. This is it's very powerful. It's very parameter efficient because you have a lot of weight sharing between the parameters. And you can end up having much larger outputs than you can have with a normal matrix multiplication. And you also don't lose spatial information, which is a very important structure of images. So these are some really nice properties. And as a side effect, you might think that this thing is really complicated. How do I take a gradient of it? Because maybe the whole thing is kind of complicated. But this is actually equivalent to a very constrained matrix multiplication. So if you take your input image and you unroll it, because with a matrix multiplication you lose that spatial structure, and you unroll your input, you basically have a few connections, like every input, every output is connected to maybe like 9 of your inputs. And that just becomes equivalent to the really, like all of the diagram with lots of arrows, but most of the arrows being 0 or missing. So this is still completely differentiable and still fits very nicely into this framework that you can plug in with all of the other nonlinearities. Cool. It's going to get a little bit harder. Another very fundamental building block is called a recurrent neural network. I don't know why the building block is called a network when everything else is called a layer, but that's just kind of convention. And this is solving a problem that is basically has not been solved in machine learning before, which is we want functions to take in variable size input, but they can only take in fixed size input. And this becomes a problem when your function is parametric, like a fully connected layer is. Because if you want a connection from every input to every output, but your input size changes, that means the number of weights you have changes. And that means that if you get a longer example at inference time, you now don't know what to do with it. And this also might be inefficient because you might have like really, really big, a really large number of inputs, and you might not need all of the power of having like every connection there. So recurrent neural network is a way to solve this problem. And the solution to this problem is recursion. So what you have is an initial state, which would just be, let's just call it h in this example, and you have a bunch of these inputs x. And there's a variable number of them, so you don't really know what like this capital T is. And you can make a function that takes in a fixed size, and because each x is fixed size, you can make that function f take in both h and x. And now you can recurse through this list by saying h of t equals the function of the previous state. Sorry, the new state is a function of the previous state and the current input. And then you just return the final one. And what this allows you to do is it allows you to, with a fixed size input, you can have it operate on, with a fixed function that takes fixed size input, you can now turn it into a function that takes in a variable sized input by applying that function a variable number of times. This is not this is like a pretty obvious insight. And you could do that with any kind of machine learning algorithm. You could like apply a random forest like an arbitrary number of times. But the cool part about this is that because this function is differentiable, this recursive function is also differentiable. So you can take the derivatives of each of the inputs. You can take the derivative of the weight matrices you use at each step. You can use that f at each step. And you get a diagram that looks kind of like this. You can think of it as applying an FC layer for each input that takes the input and the state so far. And this diagram might not be very clear, but there are many different diagrams for RNNs, and they're all equally confusing if you're unfamiliar with them. So this is kind of, the one on the left is my favorite one, because you can kind of think of it as a stateful function, except the state only lasts for the duration of your input. But the unrolled version is the version you use if you're taking gradients. So this is equivalent to just passing the gradients through this very long graph. Last complicated slide, long short-term memory units. This puts me in a really hard position because I can't not talk about them because they're so ubiquitous, but they're also extremely complicated. And they take more building blocks than I've even explained. But there is this great blog post. I think slides will be published, so you don't have to worry about that. This great blog post tries to explain it, but I'm going to try to give like a high-level intuition of them, just so, like even higher than what I've said so far, just so that you can kind of understand where it's coming from when I talk about these things being used. And the idea would be, it's kind of like an RNN. And in practice, no one uses the RNN that I've just described. It's a very simple function, and there's much more complicated versions. It's an RNN where the function is just really complicated. So this entire thing here is a representation of that function. I'm not going to get into the details of it, but it involves a lot of different mechanisms in order to make optimization easier. And the idea is that if you design this function well, the function that's applied at each time step, it can make the problem much, much easier to optimize, and you can have like a much, much more powerful function. And the key is that by having a path which is relatively simple, so this is what represents with the top path, where there's very little operations being done to it, it makes it easier to stack these things back to back, and that makes it easier to learn long-term relationships between the functions. Whew. OK, that was the complicated part. You now know 95% of the building blocks that everyone uses for state-of-the-art deep learning. With just these building blocks, you could probably do new state-of-the-art things on new domains. So congratulations, you're ready for the next part. So in this part, I want to talk about what deep learning is really good at and what you should use it on. The answer is a whole lot, so I'm going to cover just the rough themes of where deep learning really shines. But there's just much, much more to it, which I think is part of the awesomeness, because it all falls under this extremely simple framework that I've just described. I don't think that you could describe any framework as simple as what I've just done and have it solve this many complicated, unsolved tasks before 2012, basically. So convolutional neural networks. This is a general architecture, commonly referred to as CNNs. This actually means a network in this case, and not just a layer. The idea is that you take your image, you apply convolution, you apply your ReLU, your rectified linear unit, you apply convolution, you apply a ReLU, and you basically repeat this conv ReLU until you solve all of the problems in computer vision. That isn't quite true, since at the end you need to tack on some sort of output layer, and the output layer depends on what kind of input you're trying to solve. A really old school task is that it's face recognition, trying to determine whose face this is. And this is a really cool task because it makes the representations very visual. And you can see how the network learns over time. So at the first layer, when you start with the pixels, at the first layer, your filters tend to just match for edges and very simple things. So convolutions can match edges and other very simple shapes. And as you get deeper and deeper into the network, you learn more complicated functions of the input. So after that, you can start combining edges into corners or blobs. So this is still extremely simple. But after you get to another layer, somehow combining two corners the right way becomes kind of like an eye-like shape. Or if you have two corners in a blob, that becomes more eye-like. And you can build up from edges to corners to object parts and eventually into the objects that you care about. And as you get really, really deep networks, you actually have intermediates that are extremely semantic objects. For example, people have made a lot of tools for visualization of neural networks, where they visualize what the neural networks learn, And you have, for example, if you have a neural network that doesn't learn to classify books at all, but it learns to classify bookshelves, some of the intermediate features actually become book classifiers, which is really interesting. Like, it can learn like a hierarchical representation of your input space, such that these are useful things to combine together in order to make a robust classifier. And by combining, so maybe if you combine like 3 books together as well as a square, this becomes a bookshelf. So these are kind of like what the local operations do with each neural network. And the beauty of it is that it's all learned automatically for you. You don't need to program like, I have a bookshelf. Bookshelves normally have books. They have books. They have like square stuff. Maybe they're often beside flowers. This all can like happen in a data set automatically for you. And these convolutional neural networks are absolutely amazing. They just, when I wasn't joking when they save basically all of computer vision right now. It all started with ImageNet. This was in 2012. This is when deep learning actually, the entire hype train started, where you had traditional machine learning solving this very hard, very large computer vision data set, and it was kind of plateauing over the years. And all of a sudden, deep learning comes in, and it just blows everything away. And ever since then, everything in computer vision has been deep learning. Like, nothing can even compare. And recently, we've even been able to get superhuman results, which is pretty impressive, because humans are pretty good at seeing things. It's kind of what we've evolved to do. And the same architectures can do all sorts of really interesting structured tasks. So using almost the same architecture, you can use a convnet to determine, like you can break up your input space into what's called a semantic segmentation of like all of the relevant parts that you have. And using basically the same architecture as well, you can do crazy things like super resolution, where you take in like a low resolution image and make it, you can fill in the details, which is that's a pretty, not only is it incredible, even though it sounds pretty easy, it's incredible that like you can use the same architecture that takes an image and tells you whether or not there's a dog in it, to take an image and return like a new higher resolution image. And this is basically the same library, the same components. It's just very, very composable, and that's really awesome. You can also use this to solve really hard medical tasks, tasks that people could not solve before. Here, we're detecting and classifying lung cancer in CT scans. These are the kinds of things that I like to work on. And it's not only limited to vision. There's been a lot of work in language understanding. So something that deep learning is really good at is language modeling. Roughly, this means how probable is how much sense does a statement make in a certain language. So it might have to do with a question response, how are you? I am fine. It might have other things, such as, what would be a weird thing? My laptop is squishy might be a very improbable sentence to say. So a neural network could probably determine squishy is a very bad adjective for a laptop. This is a very improbable sentence. But if I said, my laptop is hot, that would probably be a much more likely sentence. And this already has some human-like feel to it, because language was designed for humans. And being able to have, like, if you can do language understanding, as in determining the probability of, like, any sentence given a context, you can, and if you do this perfectly, you can solve basically any task. And this is it's a really interesting domain where it's being applied, because if you look at how language understanding was done before deep learning was around, it was just incredibly simplistic, tons and tons of rules, no robustness to data sets. You'd have to make custom rules for every language. And now you can use the same tricks for English as you can for Chinese characters, as you can for bytecode. So that is just pretty incredible. They've obviously been much more complicated tasks. A pretty popular use for deep learning that people are really putting a lot of effort in is end-to-end language understanding from scratch. So the idea is you use an RNN to compress a sentence in your source language into a vector, like I described in the RNN section, and then you use a different RNN to decode it into a target language. And while it's not surprising that you can design a neural network that plausibly can output this, it is quite surprising that it works so well. And you've been able to have neural networks that in a span of a few grad student months, match the performance of systems that people have spent decades engineering. And nowadays, I think that deep learning systems are not, end-to-end deep learning systems are not what's used for this right now, but they're a very important component. So people still use a bit of hard-coded stuff, but it's only a matter of time. And the beauty is that, what if we have a new task or a new language? Now it can just automatically work. Like, what if we, we find some lost language from 1,000 years ago, and we have like a good amount of their texts? Can we actually learn how to translate it or understand it without any knowledge of this? And it seems like purely from data we can, and that's really cool. We don't need an understanding of something we don't need an understanding prior to applying our machine learning models in order to have an understanding afterwards. And that is just really, really awesome. I've actually been chatting with the people at SETI, the Search for Extraterrestrial Intelligence, and one of the tasks that they're doing is trying to understand dolphins. The rationale is that if we can, dolphins have language, aliens might have language. If we see alien communication, we probably want to understand it. Perhaps we can use dolphins as a proxy for aliens to try and understand them. So there's some really cool tasks that are happening there. It's not limited to that. There's some really cool things being done with art in deep learning. Actually, I think that companies have started up that their entire business model is creating awesome deep learning art, and they seem to be doing well from what I've heard. In this case, this is a hallucination purely from a convnet trained to do image classification. So an ImageNet convnet, something that takes an image, tells you like what breed of dog it is, what objects are in it. You can use it with a few tricks to create this kind of crazy art. And this was a pretty big splash. It's very unintuitive that a neural network that isn't even trained to make art actually can turn out making this kind of thing. There have been more popular use cases, such as style transfer. The idea would be you can take a neural network, still trained for classification. The idea would be classification has some priors about what images, some priors about the natural world. So what you do then is you say, I want my image to kind of match the distribution from a different image, and then you get this kind of style transfer where you can mix together these kinds of components. And while this is actually a pretty ugly example, there's some good ones, I promise. There's some much more complicated things you can do. It's not just like taking two images together and merging them together. You can do things like transforming a perhaps not super great drawing, something that you could probably do in Paint fairly quickly, into something that looks like an artist did, or something that's really awesome. And the idea would be that you can actually take these arbitrary doodles and convert them into these things that look like paintings. And this kind of stuff is really awesome, and I think it's just the beginning of the kind of stuff that we can do with neural network art. But after basically less than a year of work on this, you're making applications that are already very tangible, very awesome, this is already something that if I made this, I would probably hang up in my living room. And this has only been 1 year of work. Imagine what happens in 10 years. I saved the best for last in terms of art. We can combine our pictures with that of Pokemon. So clearly the future is here. This is one of my crowning achievements, I think. Primarily because I've done this with like dozens of people, and only mine turned out well. But yeah, I think this is really awesome. There's like just so many things to do here, and so few people are working on it, and that the sky is really the limit. So it's just really exciting on the kinds of stuff that can be created here. There have been other huge achievements. Game playing has been really big. If anyone saw DeepMind's $500 million acquisition in 2013, roughly the only paper that they had at that time was learning to play Atari games from pixels, which might be harder than it sounds, because humans have a prior of how to play the game, right? Like they have a prior that this is maybe a ball and that's a paddle and I want to destroy certain things, or they have a prior that a key opens doors, or that roads are something I want to stay on in a driving game. But a neural network is not given any of these priors. It's literally only given the pixels. Given these images, it learns to play at what is, on median, a superhuman level. And the techniques have been continuing to get better. And this kind of stuff, very similar tricks have been applied to the much more recent result of Google DeepMind's AlphaGo network, which was not that huge of a deal in the West. But if you ever talk to people from the more Eastern world, you can talk to them about, here are the achievements of deep learning. You talk about smart inbox, and they're like, oh, that's pretty OK. You talk about image search, yeah, that's pretty OK. And then you tell them about, like, oh, yeah, it also beat a world champion at Go. And they're like, whoa, it plays Go, that's amazing. And people have predicted that even beating human experts at Go would probably be, depending on the expert, 10 to 100 years off. And it happened. It just happened. It's already done. It's already that, like, humans have lost at Go. And as a side effect, Go has also caused more fear over AI safety than any other neural network, I believe. And this is probably a good representation of that. I don't know how. Yeah, that's medium clear. This is an XKCD of, like, how hard people used to think these games were. And you can see Go as basically being the last on the level of computers still lose to top humans. And not all of these are solved, but that is just pretty incredible that that's now solved. People have been trying to ask, like, if it can do this, what can't it do? Because Go is a task that requires a lot of reasoning. And these kinds of achievements have been being transferred into the physical world as well. This is Google has like a farm with like a bunch of robots that have learned on their own to grasp objects. And basically, robotics control is usually pretty hard, especially when you're trying to make it generalize. And they've been able to do that just by throwing the robots into a dark warehouse, having it trained for a while, designing a cute objective function. And it just learned to grasp things better than their hand-designed controllers did, which was pretty awesome. And more recently, actually, I think there was a video that came out last week of NVIDIA using just deep learning for self-driving cars. So the idea was, like, with just a single camera in front of your car, now your car can learn to can drive itself from learning from how other people drove. And this is a very interesting result because even Google has been working for, I don't know if it might have been a decade already that they've been working on self-driving cars using, LiDAR and SLAM and all of that stuff. And NVIDIA's, by some measures, caught up to them entirely within, I think it's been less than a year since they've been investing in this. So a lot of things, it seems to be changing a lot of things, especially these kinds of perception tasks. Because research is moving so fast, I also have to spend some time on things that are not yet practical, but may very well soon be. As a disclaimer, I've been traveling this weekend, so I'm not sure if some of these things belong in the already solved category. Generation is a big one. There's tons and tons of stuff happening in generation, so I definitely can't give it justice. There's really cool stuff in just generating images from scratch and generating arbitrary other domains from scratch. Images are just the most visual, so I have them here. But some of the coolest and perhaps most practical examples are conditional generation. Something I'm really excited about is image to text. So the idea is you take in an input image, and the output is not like yes or no, whether or not the dog's in it, but you output a description of the image. And that's like an extremely human task. It could be extremely useful. If you do this task right, it seems like there's a whole ton of possibilities. I'm very excited about taking in a medical image and outputting a complete report of it, which would be really awesome. And some people that are really excited about this, that has applications in the very short term, is, I don't know the right way to say it, but the poor eyesight community. So web pages nowadays have been pretty bad about stuff for people with disabilities. And imagine if you had a neural network that can just describe an image for you, describe a page for you, tell you what's on the page in a very semantic, summarized way. And there's also a really cool opposite problem, which is instead of taking an image and outputting a description, you take in a description and output an image, which as a terrible artist, I'm probably a bit more excited about, because instead of I can describe pictures, I can't really draw them, and these are much better already than I can draw. but that's probably a low bar. But in this kind of network, you actually take in like a sentence as text, and all of these images are generated from that network. And that's pretty incredible. Some of them are not super great, but like these birds are actually, I'd believe they're real. The flowers, not the purple ones, but they actually seem close. Like if it was zoomed out enough, I could see this as being pretty real. And can you imagine in a future where instead of having to spend millions of dollars on a movie, you just like type it up, and then a neural network just generates the movie for you? We're quite away from that, but perhaps not that far away, especially like with some focused work. And this could enable like all sorts of like new forms of creativity that people didn't even know about. While language understanding does quite well, there's deeper language understanding, which we can kind of solve in toy tasks, but it's kind of harder for real tasks. So QA, so question answering, that requires more complicated reasoning, such that if you have like a story here, and you ask something complicated, like where's the football, and you have to like go back in the story and figure out where that kind of thing happened. That thing's kind of complicated. People are very good at this task. Models can solve these simple ones quite well, but they can't do real question answering yet, which is unfortunate, but it's something that people really care about. And we're not quite there yet, but I also love how awesome this problem sounds. It's that like our machines that we have like basically spent no work on only automatically learn a shallow level of reasoning. Like that's like such a first world problem. While there's like language understanding, there's also visual understanding that is kind of unsolved. There's some awesome data set that involves images and questions, and the goal is to find an answer. And the models there are models that can do pretty okay at this task, but still very not good, and still like very significantly worse than people do. So this kind of thing is something that we can't do just yet. While game playing is solved, harder game playing is still an open problem. And you might think, harder game playing? My 5-year-old brother can play Minecraft, and he almost certainly can't beat a world champion at Go. And harder in this case means stateful. It turns out that humans are really good at remembering something, while neural networks have some difficulty with it. So the neural networks that people have been using for playing games have been completely stateless. So when you have a partially observed world, like Minecraft, where you like only have one direction that you're looking at, if you like look to the left, it forgets what was on the right. And this is something that people are still working to solve. It's the same thing with Doom, and work has been done at that, but it's far from being a solved problem, and I do believe that they're still subhuman at this task. There's some really cool stuff with automatically discovering hierarchical structure. So in language, the hierarchical structures may be clear to us because we use language. Like words are made of characters, sentences are made of words, paragraphs are made of sentences. There's this semantic hierarchy which makes it easy to break down a problem into simpler problems. But this is not the case in many domains. And there have been people who've designed neural networks that can actually automatically discover this hierarchy. And this could be really useful for tasks where we don't know how to interpret that. So something I've worked a bit on is genomics. And we really don't even know how to read genomics, right? But if a neural network can automatically break it up into like, this part goes together with that part, there's connections between here and here, this could actually help a whole lot with all sorts of different kinds of scientific tasks, just purely from data. This is when it gets a little bit computery, but these are things that I'm excited as a computer scientist. There's this model called neural Turing machines, which learns to use like a big memory buffer, which is very cool. So you can actually see like how the network writes and reads in order to copy an input. There's ways to implement differentiable data structures. So things that you thought were, instead of having like this black box of like arbitrary activations with matrix multiplies, you can actually plug in a data structure into a network, and now your network can learn to do things like pushing and popping to a stack, getting from both ends of a queue, and all of these kinds of things. And this could potentially enable all sorts of very cool use cases, such as learning to program. People have done some work where you can create models that not only can have simple input-to-output mappings, but as an intermediate in this input-output mapping, they can learn subroutines and play with pointers. And this actually makes them a very, very general computing. Like, it potentially could do all of the problems we care about if you can learn subroutines and play with pointers. Because like, that could learn abstraction automatically for you. And by putting these things together, people have been able to do things like learning to actually execute code. So the idea would be, given like code as a string and targets for that code, like what the output is, you can actually learn an interpreter for that language. And this is really exciting to me as a programming language guy. Like, maybe I could design a programming language not by implementing it, but by just showing a whole bunch of examples and the implementation automatically happening for me. Or perhaps I could just write the test cases for the language, and a neural network can generate an efficient language for me. And something else that is related to all of this stuff is, this is really early, but I think a lot of people are really excited about that, which are neural module networks, where instead of having a single architecture that you play with, you can have architectures that are, you can have a library of components, and that for every single example, you make a custom architecture, and you output it. So for example, if you have the question answering task, and you have an image, and you have a question, where is the dog? Instead of using an arbitrary network that takes in the question and the answer, you actually convert this question into a custom neural network, which combines a dog module with a where module, and outputs the answer. And this kind of thing is very early, but really promising. So that's it for the future of it. Hopefully you guys are pumped to deep learning some problems. There's a lot of software to help you. I'm not going to talk about that right now because there's a lot of tutorials out there, and I think the high-level understanding is much more important. My recommendation is that if you want to customize a lot of things, then Theano and TensorFlow are the best, because it allows you to get this automatic differentiation that I was talking about, and you never have to worry about the backwards pass, basically. And if you want to just use like the modules that I talked about, as well as a few others, Keras can solve that, and you can do a lot of these things with Keras. If you want to do this, there's a lot more learning to do, and the devil's really in the details, so I was super high level with lots of this stuff. But there's so many little things that you need to know, such as how do you perform the updates in a way that doesn't cause your parameters to grow too large? How do you initialize the parameters to not be a trivial function? How do you not overfit your training set? So there's a lot of resources out there. My favorite one is this Stanford class by Andrei Karpathy, CS231N. It is specifically on ConvNet, but it's constantly updated with state-of-the-art stuff, and it's generally very high quality. So I think it's very approachable for anyone like beginner to very advanced. And if you want to do this, you probably need a GPU or 50. I think that's it for time, so sorry I was rushing at the end, but any questions? Also, I have these slides. Which slide should I leave it on?
There are some questions here.
Cool.
So one is, how can we avoid that autonomous cars pick up human bad habits?
How can we avoid that autonomous cars pick up human bad habits? That is a very interesting question. It's very dependent on how the cars are trained. So if you train a car to copy the human bad habits, so if you train a car to copy humans, which is by far the easiest thing to do, it's not the most correct thing to do, because the most correct thing to do would be to learn how to drive optimally from scratch. That, unfortunately, involves trial and error. But you probably don't want that in self-driving cars, so we can skip that, or hard-coded rules. So what can tend to happen is if you're training it to learn from humans, it'll mimic those humans. But the idea is that if humans make mistakes, let's say humans make mistakes, and let's say humans don't make consistent mistakes. If they don't make consistent mistakes and different humans make different kinds of mistakes, or the same human only makes the mistake sometimes, and you have a neural network, that neural network can predict the expectation of what the human can do rather than the worst case scenario. So if you can think of humans as an ensemble in this case, that if you're predicting what the average of a bunch of humans can do, you can drive better than a human can. But if humans consistently make mistakes, then there's nothing you can do about that other than get more data.
I think we have time for one more. What do you think about chatbots? Is it possible to build only with deep learning?
Yes, there's actually many startups that are doing this right now. So this seems to be the next wave in startups, or like the hot thing right now, where people are trying to use chatbots to do all sorts of things for like very specific domains. It has some really nice properties from a business point of view, because your goal is to replace humans who chat. So it's very easy to like replace them with an algorithm, because the humans, if you have a bunch of them, they generate a bunch of data. So it is very plausible. It's still hard for chatbots. It's kind of like the game playing problem, where it's hard for chatbots to have a memory of what you said. So if you talk about like, oh, try opening this menu and go here and here and here, and you might have 5 sentences later, the chatbot might say the same thing, because the neural networks still have memory issues. Cool.
Okay, I think that's it. So please remember to vote, and let's give a big applause to Diogo.
Cool. Thank you.